Hello everyone. Today we'll talk about another algorithm to find the minimum spanning tree. It's called Prim Algorithm. And again, we'll use A to store all the edges of the minimum spanning tree. So initially A is empty and eventually we'll return A. And then for each vertex in the graph, we give it two attributes, a key and a parent. Each key is initialized to infinity, and each parent is initialized to null. So this is the initial condition for all the vertices. And then we randomly choose a root and set the key of that root to be 0. So we pick A as the root and set A's key value to be 0. Then we create Q, which contains all the vertices in the graph. Next, we enter the while loop. We find the vertex in Q with the smallest key. In this case, the vertex in Q with smallest key is A because A's key is 0. Then we remove A from Q. Since the parent of A is null, so we'll skip this statement. Then we'll update the attributes for all the vertices who is adjacent to A. Let's start with F. If the weight of the edge is less than the key of F, we'll update F's key to be this weight and F's parent to be A. Same thing for B. Since the weight of the edge is less than the key of B, we'll update B's key to be the weight and B's parent to be A. Now enter the second loop. A has been removed from Q, so now Q contains all the vertices in purple. The vertex in Q with the smallest key is F, since F's key is 2. And the parent of F is not null, so we need to execute this statement. We'll push the edge between F and F's parent, in this case, this edge, into A. So this is one of the edge in minimum spanning tree. And then we update all the vertices that's adjacent to F. As long as their key is less than the weight of the edge, we'll update these vertices. So in this case, all three will be updated. And now A contains the edge of AF, and both A and F has been removed from Q. Now enter the third loop. The vertex in Q with the smallest key is C. So we remove C from Q and add the edge of CF into the minimum spanning tree. And then update the attributes of C's neighbors. Since this weight is less than D's key, D will be updated. But this edge is bigger than B's key, so B will not be updated. So we only need to update D. Now A contains AF and CF, and ACF are all removed from Q. The fourth loop. The vertex in Q with smallest key is either B or D. Let's choose B, and we remove B from Q and add BF into A. Since B doesn't have a neighbor that belongs to Q, so there's no neighbor need to be updated. And the next one with smallest key is D. So we add CD into A. And last one is E. We add DE into A. So eventually Q is empty and we'll exit the loop. And A contains all the edges of the minimum spanning tree. Now let's look at the code. In the main function, I create a graph that contains the vertices of A, B, C, D, E, F, and a bunch of edges that connects the vertices. Essentially, I'm creating a graph like this. And then I call the function prim, which implements the prim algorithm. The graph is represented with a vector of vertices and a vector of edges. I've also added another function, adjacent, which will find all the adjacent vertices of this vertex. And both the adjacent vertex and the edge that's connecting to it are returned. This is the prim function that implements the prim algorithm. We have 3 hash tables. A will contain all the edges of the minimum spanning tree. Parent and key are used for computation. All the parents are initialized to null. All the keys are initialized to infinity. Then we choose A as our root and set its key to be 0, and create a queue which is a copy of all the vertices. Then we start looping. We find U, which is the vertex in queue with the smallest key. Here I use the STL algorithm of min element and a lambda function to do the job. And then I remove U from Q. Here I use erase following remove idiom. If you are not familiar with all this, you are recommended to watch my STL playlist. If the parent of U is not null, we'll save the edge between U and the parent of U as one edge of the minimum spanning tree. Then we find all the vertices that is adjacent to U. And if the weight of the edge is less than the key of the vertex, then we'll update the parent of the vertex as well as the key of the vertex. So by end of this while loop, A will contain all the edges of the minimum spanning tree. And at the end, I'll print out every edge that is saved in A. Now let's run the program. As you see, all the edges of the minimum spanning tree are printed out. Lastly, let's look at the complexity of this algorithm. This while loop is in the order of the number of vertices, and both the find function and the remove function are in the order of number of vertices. And this find function is also in the order of vertices, and the find adjacent is in the order of number of edges. So for a sparse graph where the number of edges is less than the number of vertices, which is more often in reality, the complexity of this algorithm is in the order of v squared. That's all for today. Feel free to subscribe to my channel and check out the other videos I have. Bye bye.